Can you hear me?
Yes, we can hear you.
All right. Thank you. Thank you, Jafar.
You're welcome.
I think it is time to start, and welcome to all. Just Make, I want to check whether you can hear me clearly.
Yes.
Yes, ma'am.
Okay, perfect. Thank you. Thank you. So today I'm going to have a brief exercise for you. It's going to be around 2 or around that for like 5 minutes. It's on ideal transmission lines, just a very brief opportunity to remember a couple of things. And so also what we're going to do today is to continue with filter implementation, and I want to do this as an example. I have not, couple of things. I have not assigned the project yet. I will probably do it this weekend. It's gonna take 2 weeks for you. You're gonna be asked to design all of your filters in your project. And by then, we will have everything in filters covered. And then next week, we are going to start with low noise amplifier design, which through examples as we did, matching networks have probably covered almost a good part of it. We're just going to look at how we design a low noise amplifier if the device we are selecting and the bias conditions are not making it unconditionally stable. But I think the bottom line in low noise amplifier design is just how you select the matching network. You know, that's the whole thing. So we're going to do a number of examples next week on that, and then we're going to move to mixers. So that's how it's going to go. And I think by you having the low noise amplifier designs, the mixers in place, which is going to be a relatively simple thing with a mixer, and
Dr.
and
Katani?
the filter, yes.
So this week will still be filter. Next week will be low noise amplifier.
Yes.
And then it will be mixer, right?
Yes. And so we are in week, I believe, 8.
9. I think
9 is going to be on amplifiers. 10 is going to be on mixers. And then we are going to have a number of rather system level kinds of designs. And I may, towards the end, cover a few topics not to be included in the final exam, but just for your information, maybe a couple of lectures on end-path filters, which is kind of very interesting in terms of new filter designs. I'm not going to ask you to, I will give you a homework, but I'm not going to incorporate that in the final. And then we'll see, I mean, practically by week 10.
Dr. Katehi?
Yes.
This is week 9.
This is week 9. Okay.
Well, because
9
week 8 was last week.
Okay, sorry. We lost the count. I did. Okay, by week 11, we are going to be done with the primary components of a system, all right, a receiver rather. And then from there, I'm going to do some design, some topics where the whole system is going to be in place. We're going to look at noise figure, for example, of the whole system and how we calculate noise figure, and then of the whole system then. And then I will cover some specialized topics while I'm going to do reviews, but I will do some specialized topics which I'm not going to cover on the final. So I think we are pretty good in terms of timing for this class, considering that it's a little squeezed, you know, in time. But would you have any questions or concerns about that? Okay, well, I hope I feel comfortable. If by then, you know, if you know the fundamentals of a receiver, I think by the time we finish this class, I think we'll be successful. At least I will feel comfortable that I covered the right material. Okay.
So,
Yes.
Professor, since we're talking about logistics, can I ask one question about
Of
the
course.
homework due this weekend?
Yes.
So is all that's due this weekend?
Yes. You have two.
Oh, the rework of the midterm?
Yes, yes. You have 2 things this weekend. You have the solution, like the homework, which is like solving the midterm. And then you have the critique. And it has been given to you as a separate assignment. For 2 reasons, because the homework has a maximum of 100. The critique is like a bonus. So I gave a maximum of 0, so it is not calculated as part of the total grade, all right? So that's how we do bonus in the eCampus system. But they are 2 separate assignments. I will grade, the TA is gonna grade the homework, now I will grade the critique. Okay?
Okay, great.
Thank you.
I also have a question.
Excuse me, yeah, go ahead.
For critique, do we need to solve all the questions or those that we didn't get it right on the exam?
The more, well, so I have a, how can I say? I will read here, I'll tell you how I'm gonna grade the critique. It's up to 100% in bonus. I'm gonna read everything without giving any grades, and I will identify the one that has the most complete and most, not necessarily wordy. I'm not talking about writing lots of stuff, but one that brings the whole thing together, that there's the appropriate critique. And then from there, I'm gonna grade down. It's kind of different from the homework we do, because, you know, in the homework, you have a fixed set of solutions. And then you know what is the maximum you're looking for. In the critique is different. It's like you write a narrative. It's like you write a paper. It's very hard to grade papers without having read everything first and then identify the one you consider in the class to be the top. And then, so that's how I'm gonna. Now, what that means is that if you do the minimum possible, let's assume that you have done a maximum in this class. One of the things that you will probably notice is that there are multiple solutions to the problem, that at least to the matching problem. There are multiple solutions. And I gave maximum even to those who had one correct one. Now, if somebody who got a maximum, obviously, because they got one solution, perfect, then I would expect them to write something about the multiple solutions. I mean, if the person says, oh, I'm okay, you know, I got a maximum number, that's all right. I mean, they're not gonna lose any points. They're not gonna get any bonus. Because I would like to see, as I said, critique. There was no perfect solution in this problem. I can tell you this much. If I were to submit, say, this problem to somebody who had an expectation to provide a complete solution, none of the answers were complete. So I will grade it like this. Do the best you can. Don't try to be minimalistic in your work or in your explanations. Don't be wordy either. I just want something that makes sense. And if you say, oh, this is wrong, and that's it, and this is better than the other thing, if you feel your solutions are optimal, that's a different story. I mean, do the best you can, and I told you how I'm gonna grade this one. I don't know what I'm expecting. I have to tell you, I have not done this critique in a class like this before. So I'm not, I don't know what I'm gonna see, but I don't have a standard towards which I'm going to grade. So I will read everything, and then I will read the second time and give grades for the bonus, for the critique.
I have a question on that.
Yes, go ahead.
So from what you just said, are you wanting us to critique the answer that we submitted, or critique the possible answer to the problem? That wasn't quite clear to me.
Okay, if you have submitted one correct answer. Now, if you feel, let me go from the, I don't want to complex. I don't want to, sometimes I'm thinking kind of not linearly. So in any case, if you have provided a correct solution, but only one, then I would like you to explain to me why that was not a complete solution and what would make your solution complete. All right, one solution to the matching problem is not a complete solution. And then you think of what other possible solutions there are and tell me why you would select A, B, or C, okay? And then what will help you, if you can go that far, select the right one. And why would you select one? Or maybe you already thought about the multiple ones and you just gave me one. Why did you do that? That is the kind of critique, the explanation I'm gonna have. For somebody who has not done that, has not even provided one solution, obviously there were intermediate steps that were wrong. I would like to critique those intermediate steps. Okay, is that correct? Am I
Yeah,
making
that makes more sense. Thank you.
okay? The only thing I can tell you is that there was not one person who provided a complete and full solution to the questions. Now, there were people who provided correct solutions, correct answers, but it was not a complete answer. There is a difference between correct and complete. So they still have those who got a maximum, they still have the opportunity to get a bonus. I'm not gonna take points out of your, if you don't do it, it's up to you to do it or not, all right? It's a bonus. I'm not gonna penalize anybody who is not doing it. If you cannot do it, that's fine. I mean, you just don't get a bonus, the bonus points, that's all to it. You know, in reality, I did not say that you have to. There are no penalties for not doing it. It's not like the homework where you know, even the homework, nobody is forced to do anything in this class, you know. You're not, I'm not taking points away for not doing something. That's not the case. Is that clear? I'm trying to cover the whole spectrum of possibilities, you know, that's why I'm saying all of these things. For those who may not be able to do it because of other conflicts, for those who want to do it, but they don't have enough time to put into this, I'm just trying to cover everything.
Can I ask one more clarifying question?
Sure. Yes, go ahead.
So regarding the homework 8, this is the one that's not extra credit. So regardless of how we do on the exam, like even if I got all of the questions right, for example, like I would still have to do that homework, right?
Yes, you have to do the homework.
Okay, cool.
I told you one thing. Let me just tell you one thing. No one, as far as I remember, because I made the grading myself, provided a complete solution. Considering that this is not a new homework, but this is the solution of a midterm for which I also provided. Even I did not provide a complete solution in the solutions that I gave you. All right, my solutions are not providing a complete solution. They are just providing accurate solutions. And then, and I, in reality, I did the solutions myself to be able to have a solution in front of me when I look through all the midterms. But even my solutions are not complete. They're accurate, they're not complete. So for those who have done accurate solutions in the homework, I will expect you to also provide the complete solution, because this is a homework which was a previous midterm for which I have also provided some guidance for the solutions, all right? So I will be a little more tough. I will ask the TA to look more carefully about, and this TA is very picky about things, but I will ask him to look for completeness just because of the circumstances. You know, I have some more expectations from those who did well in the midterm on how they will do the homework. If somebody makes a copy of the midterm and gives it to me as a homework, I don't know what I'm gonna do. I have to think about it.
Okay,
you know,
that sounds fair.
You know, the other thing, a lot of times, I'm a human being like you are, all right? If you, the best time to ask some of these questions, because you're asking me some questions which are very subjective, and sometimes, you know, I'm trying to tell you what I plan to do. But as you know, subjective subjective decisions, I mean, you know, I give a grade. So from the time I select the grade is subjective. Nothing is totally objective in what we do. I have solutions, those are guiding us. I mean, we try to put objectivity to the maximum degree possible. A lot of times, ask yourselves, if you were the professor, and I will tell you, you are in my position, looking at my grades, I'm the student, looking at my work, how would you grade it? A lot of times you will find that you will be more tough in your assessment than I will be. So if you want to know how tough I could be, and I'm not, because I have, you know, over the years, I have decided that that is not what really provides good outcomes. You know, toughness in grading is, as I said, grade is a tool, is the outcome, is not the goal. So that's why I have changed my perspective. But if you ask yourselves, I can bet you anything that your response is going to be more tough than, you know, it will represent a much more hard grading that I would ever do. So, excuse me, you can do that and see what you would say. And I believe if you try to satisfy yourself as a grader, I can tell you, you can satisfy me 100 times more in my grading. Now 10, maybe 100 is a little too exaggerated. Does that make sense?
I have another question for that.
Sure.
You just said you're expecting complete solutions for the homework. So just to make
Yes.
sure I have that right, you would then expect us to provide solutions for 4 different matching networks for the first problem?
Yes, and then you can tell me why you will not select some of those. Why some of those are good on paper, but not in reality, in practice.
Okay, just making sure that you were expecting like all the possible solutions. Thank you.
Yeah, a completeness, all right? When a lot of times when I say I need a complete solution, what it means in design, it means that I would like to see all the mathematically viable solutions. But at the end in design, we always select one. And we select an optimal, and you will see something about from the filters today, because there are so many considerations about what we can do, how we can materialize, especially implementation is a very important thing. And that's the one that forces us to select one design, because in reality, every mathematical solution is not necessarily producing a good, realistically speaking, a good outcome. And so that's where we are right now, all right? So, I mean, this is, I'm not expecting that you're gonna learn all of this, but I hope that through this class, you are gonna challenge yourselves with situations where you have to select out of multiple mathematically accurate solutions, one that is going to be the best as an engineer to use. So, as I said, I want to challenge you with this thought because it's an important component of the design. And I will do it as many opportunities as I can find. I will do that. So that's one opportunity, especially since it's a bonus, all right, grade. I don't want to penalize you for something that takes years to learn, but I will only like to challenge you with those thoughts. All right. I hope we covered enough on this. If there are more questions, please, during office hours. So we have some interesting things to cover today. Okay, what I'm doing right now is I'm sharing my screen. Okay, here we go. And I'm gonna start with this example that you have seen before. And last time we stopped at the design, all right, this design here that showed that, first of all, one thing that I forgot to mention last time and I wanted to mention today. The table that I used for this particular design was a table from the book that talked about a maximally flat time delay. And I know that some of you or a number of you asked, why did I choose this as opposed to just the maximally flat performance? So that gives me an opportunity to explain it. A maximally flat time delay implies the following: that your filter not only will be maximally flat for this particular design, but every frequency is going to go through the filter in a way that does not change differentially the phase of its signal. So for example, I have a signal like the ones that we're using in 5G. 5G signals have multiple channels. And yes, we're talking about one center frequency, but there is a bandwidth around that frequency. And then there are multiple carriers, one very close to the other in that bandwidth. And they do that to be able to increase the number of bits that they can put. So multiple, they code each carrier separately and so forth. And they have multiple of those. Now, if I have a filter for this signal that reaches on my cell phone, that reaches me, then what happens if my filters do not have this maximally flat time delay, like the time delay is almost constant over the band of the filter, then each one of these carriers, that each channel, as we call it, which are close, very close in frequency, but different, will have a different phase change, which we call a phase delay when it goes through the filter. So what is going to happen? In the signal, as it goes through the filter, also changes fundamentally in the way the channels relate to each other. And that introduces an error. Introduces an error when you try to down convert the signal and then get the information out. So the best filters that people are designing for these types of applications, like the OFDM kind of, which is used in 5G, and it's called OFDM modulation, is the one that uses multiple channels. So you need a kind of filter like this, because if your filter changes fundamentally, the phase of each of those channels, then at the end you have a signal that has been modulated erroneously by the filter. And that creates additional error, which sometimes is very harmful at the end. So I use that as an example. What happens when you start thinking about the phase, like the time delay of a filter, then you will see, if you look at the tables that give you the G elements between a maximally flat filter and a filter that has maximally flat time delay, you will see that you lose some kind of symmetry that you see inside in the maximally flat filter. And so what happens is that in the designs where we do not consider the time delay, you can have designs which geometrically can be symmetric. So you will see some kind of symmetry in the geometry of your filter. It's 2 o'clock. So here, for example, that reminds me, I need to give you the test, but the exercise, I'll give it to you in a few more minutes. In this example here, what I would like to show you is that this tab here and this tab here are different because it's a maximally flat time delay design, because it is maximally flat time delay. If you were to use the other table, then you would see that the design will be more symmetric, will be exactly. So the two stubs will be identical. So that's what you give up, all right? And in the design, if you have symmetry, is great because symmetry reduces the complexity. But so you lose the symmetry of your design when you go for maximally flat time delay. However, people think that that is really very important for some applications. Okay, so now I'm coming to this problem we were discussing last time, which is this one here. The problem is we have a characteristic impedance, which is 500 ohms. And why is that a big problem? I would like to show you a calculator that I found for microstrip. Okay, so this is the calculator. It has, in fact, I found it as an application. I put it, you can put it on your phone. It's like for iPad, iPhone, other Androids. So I will take the microstrip, and this is very interesting. It gives us the microstrip, the dimensions, all right? The light blue is the dielectric, the green, kind of greenish, is the upper conductor. The blue is the ground plane, both conductors, blue and green. And the intermediate light blue is them. So this one here, it has something interesting. It's very, I like it because it gives us, as a matter of fact, the opportunity to change the dielectric constant. So let's assume that I put 3.4 for Duroid. And it gives us the opportunity to change the thickness. You can see here, I'm changing it. Here I put, let's assume I'll put here in millimeters. Okay, I'm gonna put 200, 300, okay. That is 300 microns. Then I have the width, the thickness, I will leave it where it is. Now, look at the following. Look at the width. The width is W, see? On top, here is the width, up here. And the only thing I will do is that I will focus on the characteristic impedance. You see that? Down here is Z0, and on the width. The only thing I'm gonna change will be the width to see what kind of characteristic impedance is with it. Millimeters now. So I increase it in millimeters to 1 millimeter, and that goes very low to 31. Okay, now this is very high compared to the thickness, all right, which is 30.3 millimeters, 300 microns, 1000 microns, width 1000 microns, thickness 300 microns. So the width is almost 3 times bigger than the thickness. Okay, interesting observations. Look at your capacitance, it's pretty high. Capacitance is 1.6 picofarads. Your inductance, which is down here, is 1.5 nanohenries, and these are per centimeter. Okay, now let me make that very low, very low. The width, this is still the width, all right? I'm making the width very low to see how high it can go. I'm making the width, the lowest I can go in grading here, which is like 10 microns, and still the characteristic impedance 168 ohms. If I were to, you can get a lot of other calculators, all right? But let's assume that I make the thickness higher. If I make the thickness higher, what happens to the line? I reduce what? What happens if I increase the distance between between the strip and the ground?
You
What
get
happens?
decreased capacitance between the two.
Yes. So if I decrease capacitance, what happens to the characteristic impedance?
Increase.
It's bigger.
Exactly. So let's try to go the highest I can go in H. So I will try to go the lowest I can go in W. I'm still the lowest. Look at the characteristic impedance. I have only been able to go to 215. So a characteristic impedance of 500, and I put here 1000 microns. It's huge thickness, all right, for high frequencies, very high. A lot of, it's thick compared to what we are using in real circuits. But still I can only go to 215 if I make my width 10 microns. And what happens, the additional thing, we have not talked about losses. The problem with losses is that it makes the losses, the resistive losses in the line very high. And why is that? Because here I will draw for you on the side to see. If I have a very narrow line, this is my microstrip. All right. If I have two different types of microstrip, same thickness, this is a big one, this is a narrow. In the one that is wider, the current will distribute like that in reality. So it is flat in the center, it has those the edges goes high, and it's called edge effect. When I have a very narrow, the current will go like this. It will not have the chance to go to become any flat, all right, if it's too narrow. So in fact, if I can go here, and if I were to show how the current will go, practically it's gonna be a very, here, very narrow and high at the edges. And for the current to be able to even have this kind of distribution, in reality, is not gonna go this low down at the center. It's gonna probably look like this. Because most of the current is going to distribute at the edges, percentage-wise, all right, in the narrow. You will have very high losses in the narrow microstrip, and you can prove that mathematically, which is not this in the scope of this class. But this, so your resistivity or your resistive losses in this will be much higher than the resistive losses here. So narrow microstrips are pretty bad deal if they're too narrow in terms of loss. The other thing they do is that if you have a microstrip that is this narrow, your inductance increases. And if you have any inductive parasitic effects, like in a capacitor, if you're going to use a narrow thing, a narrow section of line like this to develop a capacitor, as you will see later, then that is going to give you a very high parasitic inductance. So we always try to accommodate to develop the design, so we accommodate our concerns between too wide as a thickness, which makes your capacitance too high and your impedance too low, and too narrow as a width. I meant to say width. Too narrow as a width, which is going to make your losses much higher, and then your parasitic inductance high. So you're looking in the middle ground between too wide and too low. That's why too narrow. That's why we are trying to avoid very high impedances and very low impedances. All right. So if I were then to be in that kind of design here, where I used, if you remember, this here assumption. In the previous design, I used the assumption that if I have a section of line, which is 1/8 of the wavelength, then my input, if it's a stub rather, that the line is terminated in an open end, and it is 1/8 of the wavelength, so that's a stub, then the input impedance is equal to J, the characteristic, times the characteristic impedance of the line, all right? So that is what forced us to say, well, in order to be able to do this, I have to have a stub that has a characteristic impedance of 500 ohms, which is not something we want to do. So to be able to avoid this, which parameter in this stub we can use to avoid having too high of an impedance? What do you think? It is the length of the stub. If we relieve ourselves from this constraint that the length of the stub has to be 1/8 of the wavelength, then we can find another length which is going to give us what we want. Do you agree with that statement? Can you hear me?
Yeah, that makes sense.
Yeah. Okay. So what did I do here? I said, okay, let's assume that my length, the stub is still open, like you see here. I have a stub which is open. The only reason I want the stub there is so I can realize that I can realize a shunt capacitor. Remember from the filter, I have to realize my shunt capacitors that they were here before, if you see from the previous lecture. So the only thing that I'm gonna do is to find this so that the input admittance at the stub is equal to this one. That's what I want. Okay. Of course, I put the J because in the when we use the transformations in the book, you know, the J is not there. And that's why I want to use also try to get connected with the book as well. So what did I do? I took the transmission line formula for an input admittance and for any general load. And I express the load as an admittance here. Okay. And this is the formula we've learned from ideal transmission lines. And then now I have an open end. What happens in an open end to the load? In the form of an admittance, then the open end has a zero load as an admittance. Do you agree?
Yeah.
Okay. Then if I plug Y sub L in here, what I get out of that is that the input admittance to a stub like this is J tangent of beta ds. So now I have something to play with, which is the length of the stub. Okay, and that tells me that since my input, remember where the 500 started from? The 500 practically was the Yj that I wanted to see. If you go back in the design of the filter we have looked at last few times, the Yj practically was 1/500. That was, so Yj from the design of the filter had come out to be 1/500. Okay, so now for me to satisfy this, all right, for me to satisfy that, let me write it here. Then I can solve this equation. Okay. Now, we are going now to a different problem. From one problem, we go to a different one. Because 500 is too big, And ZOS, we can select a characteristic impedance. So if you go for 50 ohms, let's assume that you select now ZOS select to be 50 ohms. If we select that, then 1/50/500 becomes 1/10. All right. So the inverse tangent of 1/10 will give us the B beta ds, the product. And then we find that the value, since a small value, since tangent varies like this, that the areas that I have here in purple are the ones that will take me in terms of the inverse tangent. All right, so my x, which is nothing else but beta, you see that here, my x, which is that practically here, is going to be very small, depending on the value of ZOS. The smaller the ZOS and away from 500, the smaller this value, which in fact tells me that the higher the characteristic impedance of the stub that I'm getting, the higher the characteristic impedance of this stub here, what happens? The smaller the length below 1/8 of the stub. So as I go down and away from 500, yes, I can get the input admittance of the stub to match the value that I want, but my length becomes smaller and smaller. And what is the problem if I have a stub that is too small? And microstrip is not going to operate that well, because practically in microstrip, what you're going to have with a very short stub is going to be something like this. It's not going to even look like a stub. If you consider all of the fringing and the parasitic effects from the corners and everything, that does not, it's going to look like a small change in the width, but it's not going to work. So we cannot make it too small, all right? And that tells us that maybe that approach for the design was not very good. So what that tells you is that using the various trade-offs between especially implementation and what you want to do, you may find after a long effort to design something that the design approach you took may not be the right one. So that may not be the right way to do this. And as a result from here, next time we're going to start, and may start today, but next time we're going to do this stepped impedance low pass filter to see, in fact, another way of doing a design. In fact, it's a bandpass that I have created here for you, bandpass. We'll finish that on Saturday. But I want to give you an idea of what kind of trade-offs you're gonna face in your project. Because at the end, your project is not only to give me, I will not ask you to give me mathematically accurate designs, I will ask you to give me realizable designs. Okay, so that here I wanted to show you the trade-off. Now, at this, yes?
Would you go over the purple equation? How did you conclude those? Yeah.
Okay, so look at this X. So X is what is beta ds. Okay, and ds in lambda is going to be 2 pi ds in lambda. Okay, So your ds in lambda here, which is your electric, so let me see the electric length. So ds here in lambda. All right, not in physical units, but in electric units, which is the wavelength. Then your ds is going to be from here in lambda, obviously, in lambda, is going to be x over 2 pi. You see that?
Yeah.
Down here, I included the lambda because I went back to the, it was not explicitly, I wanted to do it explicitly. So, but in that up here, I will do, it is in lambda. If I want to be careful so I don't confuse you, that I will put it here and I will have that in everything. Okay, that's how we got that. Okay, any other questions with that? Now, what I will do, I will give you the exercise. It's gonna be just 5 minutes. So we'll go, let me go here. Audi. Okay. Hmm. Okay, this is on transmission lines. It says, please identify all right, you see ALL, all the correct statements. And in fact, this one is not, don't look at this square, well, see, I had to write it up there because there are some problems with the typing. I had to write it there and then copy down. So in fact, I can edit it right now so you're not getting confused. There. Okay, save. Okay, now this one asks you if you have a transmission line which has an L and C, and this is the inductance and capacitance per unit length, if you remember. I would like to see whether you remember the relationship between the characteristic impedance Z naught of the line and L and C and beta, which is the propagation constant, and L and C. And mark all the correct answers, and I will assign it right now. All right? And then when you finish with that, you're done for the class.
Is this for a lossless line or a distortionless line?
I did not give anything about losses. All right, obviously. So in an ideal transmission line, obviously, yeah, without losses, but thank you for mentioning that so I can clarify it. And out of there so you don't see what the colleagues are doing. I don't want you to get mixed up.
Professor, what is the app called that you were referring to earlier, the calculator?
What is called? Let me tell you. 1 second. Use apps. It's called. I don't know how it is, but I found it. You see this picture? Let me see. I need to do that again. Start. Just a second, I'll show it to you. Do you see this little picture down at the one that says impedance? That shows the three kind
Yes,
of one.
yes.
Yeah, that one. I don't know. I don't remember. This is the only one I found from the app.
Okay, thank you.
Sure. There are many other ones, as a matter of fact, but this is one I can download.
Okay.
Dr. Katehi,
Yes.
do I have access to the class notes we talked to today?
Excuse me. I'm sorry. Could you please repeat?
Do we have access to the class notes we
Yes, I will
discussed?
upload them now. And in fact, I will also upload the I'm working on those. I think they will be ready. I'm trying to, the videos from the last 2 times, but yeah, I will upload the notes.
Yeah, because I need to look at the notes in order to, yeah.
Yeah. Oh, you look
Really?
to look them now? Okay. Yeah, sure. You mean the notes from today?
And on Monday.
You need to look at this to solve the what,
Yeah, because my notes are not very.
you don't, there is nothing on this transmission line for the, if you are talking about the top hat, you don't need your notes, but it's online. But there is nothing there. Look at the previous, it's the same kind of file I had for Friday.
Oh, Friday.
I can upload it again. Let me see. It's the same. You're talking about this one? This is the one we had.
I'm just looking for beta.
Yeah, this is in, if you go on, well, this is fundamental, so it is in the transmission line. We did that long time ago. So you may have to go to your transmission line on, if you go to the modules by topic, look under transmission lines. Or look at your book.
Okay.
Oh.
Dr. Katehi?